very happy to be doing this first CHATS event here at Culture Café. I'd like to thank, as I said earlier, this is really possible because of this workshop, scientific workshop that's currently taking place at Notre Dame, organized by myself and Professor Yuhsin Tsai, which is why we have lots of world experts in particle physics and cosmology here. And so I'd like to thank the Notre Dame Department of Physics and Astronomy and Notre Dame College of Science for their support putting on that workshop, and especially Professor Yuhsin Tsai for funding specifically this event, as well, of course, as Stephen and Mary Merriman very sincerely for inviting me to develop this series of events with them and have some science slash art activities here. So let me say, as you know, the event is free, but a great way to support the Merrimans is with Culture Café right outside. Mary makes lots of fantastic soup and baked goods and other things, and I especially like Christopher's tea lattes are a favorite of mine. Christopher the barista actually volunteers his time to be a barista here. So I always tip generously.
For the Playhouse event.
Oh, okay. Yeah. Okay, maybe not right now then. Right, yes. Good, if you're so inclined, you can also donate directly to Merrimans Playhouse, which is the nonprofit that has this space that we're using this evening. Okay, so without further ado, I'm happy to introduce our special guest for this first edition of CHATS, Professor Dan Hooper. So Professor Hooper is the director of the Wisconsin Ice Cube Particle Astrophysics Center at the University of Madison, or Wisconsin-Madison, where he started actually just this academic year after many years more close by at Fermilab and the University of Chicago as a professor. And Professor Hooper is a celebrated researcher in astroparticle physics and particle cosmology, has a very deep understanding of many of the important problems, all of the important problems perhaps, in this area, and is also a leading science communicator in these fields. He's authored 3 books for the public, most recently At the Edge of Time, exploring the mysteries of our universe's first seconds, and we're grateful to Rainlair Books for partnering up with us to have his books available outside in the library. Maybe you can be willing to sign some autographs afterwards if people are interested in. Great, and you've also written many articles for popular science publications. You've given lots of prestigious public talks. You co-host a hit podcast, Why This Universe, which I highly recommend. It's at a really fantastic level where you're really getting into it. You're saying real things, and yet in an understandable way, which is a tough balance, but really great. And Dan is also a member of the Spectral Distortions, the universe's premier physics punk band, which we'll maybe get to a bit later.
The best of all of them.
Yeah, most important, Laura. But Dan, thank you so much for being here.
Thanks for having me. This is great.
So, where to start off, I think an important overall takeaway that one should have from modern cosmology is just the absolutely enormous amount that we have learned about the history of the universe and everything in it. So, for people without the background here, I thought maybe we could start with, how is it that cosmologists can use just observations of the sky to learn all these important things about the past?
So, let's just start by considering how recently it was that we do nothing about this, okay? So in, 1915 or something, if you went to some physics department and asked, so how could the universe itself, not the things in the universe, but the universe itself, how could it change with time? How might it end one day? How might it have begun? They would have looked at you like you were crazy. Right? This is just not a topic, a suitable topic for physicists. It's not something that physical sciences can address. And they thought that because Isaac Newton had set out this whole vision of what space and time were. And to Isaac Newton, space doesn't do anything. It's a completely static backdrop. You can't use any verbs with space. So space doesn't change, space doesn't grow, space doesn't expand, space doesn't contract, space doesn't curve, space doesn't work. All that stuff, it just sits there. And if space just sits there, it's really hard to imagine space starting or ending. So physicists didn't think about these things. Then Einstein comes along, general relativity is born, and suddenly space has a very more active role in our universe. It's not a static backdrop. At the core, at the foundation of Einstein's theory is the idea that when there's energy in space, that energy influences the shape or geometry of that space, causing it to change, causing it to warp or curve, and those changes, those curvatures or warpness, whatever, is the stuff we call gravity. The reason things move in arcs around massive objects is because the geometry of space is changed by that stuff. So, but if space can change, then it can expand, and it can contract. In fact, if you take Einstein's theory into space, it really has to be. It can't be static. Space should be expanding, it should be contracting, and 10 years later we measured it was expanding. And if it's expanding, then that means in the past it was smaller, and it was hotter, and it was denser, and pretty soon you reach a point where you at least extrapolate to a point in history where the universe was really hot and really dense, and that's the Big Bang. And yeah, it took 110 years to get from there to here. I would say by the mid 1960s, we're pretty sure a Big Bang was a real deal. But we've, in that last 50 or so years, we've gone from being pretty sure there was a Big Bang to knowing an awful lot about the Big Bang. We can tell you today with incredible precision what the universe was like 13.8 billion years ago, when it was dense and hot and concentrated. We can't go back to the very, very beginning reliably, but from about, say, 1 second after the Big Bang to the present, we have a pretty good picture.
That's remarkable. I mean,
yeah.
Amazing that we
it
can...
sounds like fiction, right? It doesn't sound plausible,
right.
And yet here we are.
Right. Yeah, we don't have to, tell folklore about these big, important questions anymore. We really have an observational program, and theoretical program to understand the empirical. It is really mind-blowing.
I agree.
Yeah.
I mean, this is why I do this for a living, right?
Yeah.
I mean, I was never a very practical person, okay? This will probably come up later, but I didn't go to college to be a scientist. I had no interest in science. When I started, I was a music student, so this is right in my wheelhouse here. And but I stumbled into physics because I learned about stuff like cosmology. I learned about stuff like quantum physics, learned about relativity, and these were the most exciting things I'd ever heard about. And I didn't think I had a career ahead of me there. I thought that was an incredible long shot. And even if it hadn't worked out, I would not have regretted those years of studying it. I'd be happy to, have some, day job now and still get to know what I know about the universe. I would take that trade in a second. I just got really lucky that it worked out.
And before, more questions in that direction as well, but I thought we could maybe just linger on sort of the observational side of how we know as well. I mean, just from the basic fact that the speed of light is finite, there's this amazing fact that we can look into the past by looking at things at longer distances. So that's, of course, we've had these theoretical developments that are the framework in which we understand these things. But really, it's not just playing with pencil and paper. We've confirmed all of these things through observations, which is amazing stuff.
And like, an archaeologist or historian or something does this by having objects like persistence in time. We do it by the finite speed of light, right? But it's the same idea. It's basically cosmic archaeology. So I can take a telescope, or rather one of my observer friends can. I don't know how to use telescopes. And they can look at something a billion light years away, and they know what that part of the universe was like a billion years ago. Ignoring the speed of light, that's complicating, but whatever. Mostly what I said was true. And if you look 10 billion light years away, you find out the universe was like even earlier than that. So the finite speed of light allows us to kind of get images of the universe when it was very old, not very young, I should say, very young, a long time ago.
Yeah, and we especially have this fantastic data in seeing the afterglow of the Big Bang, just 300,000 years or so after it was formed with the cosmic microwave background, which again, detecting that tells us remarkable about the early universe.
And not just detecting it, but studying it in hyper precision, right?
Yes, absolutely.
So this was light so for the first 380,000 years after the Big Bang, the universe was filled with a bunch of charged particles. So it was like electrons, protons, and other things like this. And light cannot travel through that environment. For the same reason light can't travel straight through the sun, light could not travel through the universe during that era. And then the universe got cold enough that those electrons and protons and things started to bind together to make electrically neutral atoms for the first time. And suddenly, instead of being a plasma that filled all of space, it was a gas. And I'm looking through gas at all of you right now. Gas is more or less transparent. So for the first time, all of this light that had kind of been pent up, in the plasma that filled all of space, got liberated, traveled outward in all directions, and it's still traveling in those straight lines ever since. In fact, right now in this very room, in every room in all of the modern universe, there are 400 and something of those photons in every cubic centimeter from the Big Bang. We have incredible telescopes that study this. We detected it in the 60s, and then we measured it better and better and better and better. Today we can measure its detailed temperature variations, better than 1 part in 10 to the 5 in all the directions of the sky. And we can use that information, along with a bunch of theoretical understanding, to tell you things like how the universe has expanded over time, how its temperature has changed over time.
What particles exist?
What kinds of matter and energy exist? All this sort of stuff. It reveals evidence that there's dark matter, dark energy, and a bunch of other mysterious stuff that we don't really understand yet. But it's an incredible treasure trove. If I had to have only one piece of cosmological data, that would be the one I would keep.
Again, just amazing how much we're able to learn about things that very recently we would have thought we just can't have any picture of. You bring up a lot of things that I want to talk to you about. Maybe staying broad for a moment. Do you think that there are lessons to take away from cosmology for people's everyday lives? Or maybe I can ask, has learning cosmology changed how you conceptualize parts of your existence?
Yeah, absolutely. So, like most people, when I was younger, looked at the universe for moral and otherwise forms of order. I expected things to be the way they are for a reason, there to be purpose in the universe. And the more I have learned about the physical cosmology of our universe, the physical laws of our universe, hey there, the way that our universe works and the laws it follows, the more I see no signs of purpose at all. And you might think this is pessimistic or something, but it is not. It is purely liberating.
Yes.
If there's not purpose, we can live for any purpose we choose. We create it.
Yes.
And the universe does not impose it upon us. The universe leaves us entirely free to decide for ourselves what to make sacred, what to make important, what to value. And to me, that's the most important way in which my understanding of the universe has impacted the way I feel and think about life.
About very big questions that everyone that has an interest in understanding. And I think it's very important, and sometimes people don't appreciate that this lack of purpose, as you say, shouldn't lead to some nihilistic sort of worldview. I mean, for me, appreciating that all matter on Earth, all matter has some shared history over cosmic times, from the earliest formation of atoms to their reprocessing in nuclear processes in stars, to the point where you can have the sun exist for a very long period to give energy to rocky planets that surround us. And I think for me that's led to a greater appreciation of how connected we are as humans.
There's so much to experience awe about. Like, I mean, I like to take off my wedding ring every once in a while and just stare at it and go like, this thing was made almost entirely in the core of an exploded star. Like all these atoms. That's where those atoms came from. Like, that's the only way you make silver in this universe, right? Or approximately. And that's this kind of glorious, all-pervasive oneness of the universe. There is nothing in this universe exists independently of anything else. And that's without even going into the weird quantum stuff about everybody's waiting for people having sex. This is an amazing universe, and the more you learn about it, the more there is to find wondrous and weird and inspiring.
Yes, and like you say, there's this, like, rather than some grand purpose, there's this contingent element to things. You could very well imagine a universe that at the fundamentals is like ours, but where you don't have stars.
Sure.
You don't, and as you say, this is a process that takes the universe hundreds of millions of years to build up elements of the sort that exist on Earth. There are all of these sorts of things that have happened that conspire to make human life possible. It's again like a really awesome, as you said, thing to appreciate.
There are some amazing cosmic accidents that have happened in this universe. The origin of life is certainly one of those. And I'm very open-minded to the possibility that you will find life elsewhere in the universe if you look hard enough. But it doesn't seem to be super common, right? And the conditions for life are pretty special. I would guess it's pretty rare.
Yes.
And it happened here. And furthermore, it didn't just happen here, but it evolved through a series of ways to lead to things like, human intelligence and consciousness. Consciousness I consider like beyond incomprehensible mystery still. I don't understand consciousness.
Currently, but not in principle.
I don't know. I'm open-minded to understanding it one day, but I'll say I don't understand. I can't envision yet how we're going to understand it that way. Okay.
Let's not get
that's not. But
why not?
Somehow the laws of physics, though, led to a configuration, an extremely complex configuration of atoms like that fill this room and lead to the plane of jazz. Like that's just ridiculous. It seems implausible, and yet here we are.
The development of, like, just as one small part of that, the development of human sense organs, or animal sense organs, really, to allow us to interpret this data that just comes from the world of light, of pressure waves, of various chemicals in terms of things that we can then, find beautiful and find our own meaning in, is also amazing, and a process that took billions of years from the beginning of life on Earth to get to this point.
Life started almost immediately after the earthquake, right? As soon as we stopped the bombardment.
Right. Which is another reason to think it must also happen elsewhere. I'm going to embarrass myself. The Milky Way, it's 100 million stars? Is that the right order? Or am I off by 10 billion?
Well, we have about 100 billion.
100 billion, sorry, billion. That's
it's a big number.
An amazingly large number, right?
That means you could have a very small probability of life and still have a lot of it. Not to mention the fact that there are a trillion galaxies
Right.
in the
Right,
observable
right, right.
universe.
Yeah.
Multiply those numbers together, it's a big one.
Good. Now, good. Sorry, these questions are great, but I also want to spend some time on more particular questions toward your expertise. And one thing that both physicists and non-physicists are very curious about is dark matter. We've been discussing this as a topic of discussion at the workshop as well. These are some additional particles which so far we've only understood through their gravitational interactions. And like you were alluding to earlier, we don't know exactly, say, what this is, but I think often what isn't emphasized enough is that, thanks to decades of great work by experimentalists and theorists, we know a huge amount about what dark matter is not.
Yeah,
right?
we're very good at that.
Yes. We have lots of information about which interactions it cannot have, or in some cases what masses it can't be, what the nature of it in terms of a physics theory can't be. And so the question I want to ask, and this sort of came up at the workshop earlier, is to what extent do you think we're zeroing in on the identity of dark matter? And how optimistic are you for further understanding of the nature of dark matter over, say, our lifetimes?
All right, so I'll answer your question, but I want to say a few things first. So when we look at the universe, we have a lot of ways of using gravity to try to estimate how much stuff there is out there. So if I wanted to know what the mass of the planet Mars is, the best way to do that is to look at its moons and how they orbit around it. Deimos, Phobos, and Deimos. And from those orbits, you can work out the mass of Mars. That's where you look in the back of an astronomy textbook. You look at the mass of Mars. That's where they did that number. So you can do that with things like galaxies. You can do that with the Milky Way. You can look at the rate at which stars move around the Milky Way, or gas, or other things. You can do this with galaxy clusters. You can do this with all sorts of different systems. And everywhere we look, we find that there's 5 or 6 times more mass than we can account for with visible stuff made of atoms. So the atoms in our universe, protons, neutrons, electrons, and all the ways that they combine, make up maybe 15% of the energy density in matter of our universe. The rest of it is something else. We don't know what it is, so we give it a name. We call it dark matter, but that doesn't mean we understand it. It's just a placeholder. But as the name implies, dark matter doesn't appreciably radiate, reflect, or absorb light, so we don't see it with our telescopes, we just see its gravitational effects. Now, as Seth said, we speculate that it's made of some sort of new kind of particle, something we don't know about yet, something that doesn't interact very much. And we have all sorts of ideas for what this might be. It's not, like, I get emails all the time from people saying, like, here's an idea for what dark matter might be. I don't need any more ideas. We've got plenty of ideas of what the dark matter might be. Thousands and thousands.
But it's important to say that we have good reasons to speculate in this direction. It's not pure speculation. It's very hard to imagine something that isn't, in some sense, a new particle explaining the cosmic microwave background of the observation.
I totally agree.
Just to explain
that or maybe little black holes or something. But almost. Yeah. So there's some kind of particle that makes up the dark matter in all likelihood.
Yeah.
And we have a bunch of ideas for what it might be, and we have a bunch of ideas for how to test it. So we do things like we run the Large Hadron Collider, the world's most powerful particle accelerator. We try in those collisions to create dark matter particles. So far we haven't seen that. Well, we look. And we learn what dark matter isn't by doing that. We go to deep underground laboratories, and usually old mines, like old abandoned mines, or sometimes not even abandoned, but some old mines. And you build devices that if dark matter particles travel into them, they might interact with them and detect them every once in a while. And unlike other forms of particles, dark matter can go straight through the earth without noticing it's there, so it gets to the underground laboratory. And we look for dark matter this way. We're really good at it, but we haven't seen it. Okay. We build telescopes to to look for the kinds of energetic particles that might be created if dark matter is either maybe decaying away, or maybe when dark matter particles interact with themselves, they might transform into visible forms of energy, and we look for those. We've looked quite powerfully, and I would say for debatable whether we've seen it in this case, but we haven't been convinced yet that we've seen it. Now, if you ask if I'm optimistic, I'm going to linger on that last point of it, because there is this gamma ray signal. I found it in the Fermi data 15 years ago. It's close and dear to my heart, but I think even I know it sounds like I'm harping on my own thing or whatever, but I look at this honestly and without I think with some degree of detachment, and I still think this thing looks like what dark matter is. It has the right spectral shape, and it's the right brightness, and it's the right distribution of the sky of dark matter. I think there's a reasonable chance, certainly not proof, not certainty, I don't know, but a reasonable chance that we're going to look back on this one day, maybe one day soon, and think this is when we found out what the dark matter was. Or not. Both are reasonable possibilities. That's how science is. So I'm contingently optimistic that we'll figure out what dark matter is, but it rides on this. If this turns out to not be real, it could be a long game. It could be a long game.
And what sort of observations are needed to, or theoretical understanding, needed to cross-check, to double-check this?
We just need a really good gamma ray telescope that can see if the same signal comes from little galaxies we call dwarfs. If we see that, game over. If we don't see that, game over the other way. It would be really, really definitive, except for the paper I will record in that says the opposite. But other than that, that's the caveat. Other than that, is what I said is true.
Okay, interesting. And another question before we switch to maybe a little bit about music. Another question about like the sociology of this sort of physics. How surprised should we be, do you think, that dark matter exists? Obviously, a century ago, when we first found the evidence, people were extremely surprised. But you could imagine that the order of our understanding could have gone the other way. Maybe we first, in some alternate timeline, first we had already understood quantum field theory and the standard model, and beyond the standard model physics, and then we go out and look at the sky and we find that there's some other particle. Would we be so surprised in such a case, now with the benefit of hindsight of all of this theoretical understanding?
Here's how I think about it. We know the list of particles that exist in nature. I guess there are 20-ish of these things. Some of them have electric charge, some of them don't. Okay? The ones with electric charge we can see because they interact with light through the electromagnetic force. Some of them have something called, what we call, physicists call color, not to be confused with the thing that light has, but this other thing kind of like electric charge. The ones that have that we can see because they interact through the strong force, what we call the strong force. Some of them have this thing called weak hypercharge, and you can see that through other things. But lots of these things don't have some of these things, okay? Like these charges that different particles have are not universal. And it is incredibly easy to imagine that there exist some of these particles that don't have those things. Okay? Just like there are some things that don't have electric charge, it's really easy to imagine there are things that also don't have this strong force or the weak force acting on them. And what would those things be, at least if they're long-lived? They'd be dark matter. So I'm not even a little surprised that our universe contains a fair amount of dark matter.
Right. Even though it's still a mystery, we really want to get at what the exact nature is. We shouldn't think that this, poses a deep foundational problem for our frameworks of physics.
There's no reason to panic over this one.
Right.
There are things we don't understand about physics that you might want to panic over. This is not one of them. This is one of the things that, if we keep looking, I'm pretty sure we'll solve this eventually.
And in particular, we already know, as you said, of some electrically neutral particles, neutrinos, that in fact make up some small fraction of they behave like dark matter. They're not the dominant component of dark matter. We've determined that.
The tiny fraction of the dark matter is made into
So that there are additional particles like this it is not at all. I think it's very weird to think about.
Yeah, very easy to make.
Good. Okay, so switching gears a little bit, maybe just generally, can you tell us a bit about how you got into music and, well, maybe actually the more interesting, well, the other direction, how you got into physics from music, but also into playing physics-themed music.
So, all right, so, I mean, I played a bunch of instruments as a kid, so, like, I had a background in playing, piano lessons and all that stuff, and also, school band, saxophone, those sorts of things. But, when I was taking those piano lessons, they kept giving me, classical sonatas, and I never enjoyed that stuff. But then I got this book of, like, boogie-woogie stuff, and I could really get into that. The first time in my life I remember really connecting to music, I was in my dad's truck in rural Minnesota driving somewhere, and I was probably 6 or 7. And on the oldies station was No Particular Place to Go by Chuck Berry. And I was like, I didn't know what this was, but like it was the first time that I was like, this is amazing. And I didn't say anything, I didn't even mention it to my dad. I just sat there in silence, and I scrolled it away in the back of my mind for, however many years it's been. But, it struck me like a hammer over the head, how powerful that can be. And later I found that I was really into jazz and blues and traditional American music of all forms, including early rock and roll and sometimes later on. But, I turned to be a teenager, I developed quite a rebellious streak, you might be surprised. And I pick up the electric guitar, I start playing heavy metal and things like this. And I joined a bar band, right? These guys in their 20s and playing like 3 nights a week in the local bars, playing AC/DC covers and stuff like this. It was a lot of fun, but this did not make for a great scholarship. Okay, I was not a great student. My high school guidance counselor said I would never cut it in college. Yeah, that happened. And I don't even know how many days I missed in my junior and senior years of high school, but it was many, many dozens. And I certainly never considered being a scientist. I took some science classes, but I took them the way I took all my classes, very absent-minded, very truant, very uninterested. I wanted to be an artist, I wanted to be a musician, I wanted to be a creative. And to me, at that time in my life, science did not seem to be a way to express one's creativity. That just shows I didn't know what science was.
Yes.
So I get to college, I'm intending to study jazz performance, and I'm just frankly not good enough. Okay? Like my chops would never be good enough to have a career doing jazz. At least that's what I thought. It's probably true, I don't know. But I looked at all these people who were graduating, the same degree I was gonna get, and they were, becoming insurance salesmen and playing weddings on weekends, and like, I could do better than that, doing something else, right? And I can keep playing music, and I have. I've almost, throughout my entire adult life, been in at least one band at any given time. There have been a few months here or there I wasn't, but I've been playing music consistently throughout my whole life. So I didn't have to give up music, I just gave up formal training in music. And I decided to go out to my university and just try a bunch of different classes. I took classes in history and economics, I took one in philosophy, and in the end I just I'll just be practical. I'm pretty good at math. I'll go do this engineering thing. There are lots of jobs in engineering. I'll have a nice house one day and stuff like that. I wasn't excited about it, I really wasn't. But it seemed like the thing to do. But the best thing about being an engineer is they make you take modern physics. Yeah. And this is the first time I heard about quantum physics. It's the first time I heard about relativity. And by the time that 1 quarter was over, I'd already officially changed my major. I never took another engineering class. I don't even know if I finished my engineering classes that quarter. I might have dropped them. But I was all physics at that point. I threw myself into it. I did nothing but read physics books and play music. And everyone thought I was out of my mind, you know, but and nobody said that you have a legitimate shot of a career in this. I'm a junior in college learning about physics for the first time. And yeah, it doesn't make any sense. But I worked really hard. I have some talent for it, I think. And I worked my way up and went to a pretty good grad school at the University of Wisconsin. Then I went on to Oxford and then Fermi Lab at the University of Chicago. Now back to Madison. And it's been a pleasure. And all of it's been fun. All of it's been thrilling. Yeah, I feel very lucky to have kind of stumbled into something that is such a good fit for me and my personality.
And so I want to return to something you brought up. You know, I think often people have this idea that scientific pursuits and artistic pursuits are just entirely unrelated and completely different ways of thinking. But indeed, I think most, if not all, of the physicists in the room would feel, at least sometimes, that there are elements of creativity in pursuing physics research as well. So I wanted to ask about what similarities you see as someone who is also very involved in creating music. What sort of similarities or contrasts do you see between these different elements of creativity?
Well, first of all, like, not all scientists are creative, but all the good ones are.
Yeah. And we've only invited good scientists here.
But I mean, like a lot of people, when I was taking my high school science classes or whatever, learning about science, or even college science classes, I didn't think it involved creativity because they gave you prescriptive problems to solve that have been solved a million times by other people, and they give you a cookbook formula to do it, and you know, you memorized a bunch of stuff, including a bunch of steps, and yes, you had to understand things, but it didn't seem creative. What I realized at some point is being creative in science is analogous to songwriting in music or improvising. So if you're just taking that, you know, Mozart sonata that you were given by your 4th grade piano teacher and just learning to play it note for note, that's also not creative. And nobody would say music isn't a creative pursuit. It's just, you have to do it right. You know, so you have to improvise, you have to write, you have to make it your own, you have to play it differently than the page tells you to. And the same thing is true with physics. Nobody can make a really good career for themselves just by doing what's prescribed to them in physics. They have to find new solutions to problems. They have to identify problems that people didn't even know about before. They have to find new ways of calculating things that literally no one's ever done before. That's what physics is all about at the research level. I remember thinking it was super intimidating when I was starting grad school. You know, I really never had a creative idea in physics yet. And people told me, like, well, to get a PhD, you have to write a thesis about something that no one's ever done before. You have to come up with it on your own. Like, how am I going to do that? But then I thought back, that's exactly how I felt before I wrote my first song. Like, how do you write a song? I know how to play other people's songs, but how would I ever know how to put these things together in a new way? Like, why would it be good? How would I know what a good or a bad song is like, etc.? And then you just find one day you can do it. And you do it by learning a bunch of other songs, intuiting what makes those songs good, and then start to do your own thing. The same thing is true in physics. It's exactly, you read 1,000 papers by other people, you learn to understand them, you do a bunch of calculations, and pretty soon, oh, I wonder if this was different, what would happen? And it turns out no one's ever thought about it.
Yeah, it's very in line with my experience in physics research. Maybe even this element of creativity is even amplified in this field of theoretical particle physics, which is model building.
That's the extreme version, right?
Right. Where really we are, the goal is to come up with some theory of how the fundamental world works that no one has written down before, and a theory that needs to be consistent with all available data. I mean, sometimes I even think of it as like a very constrained form of storytelling.
Yeah.
You want to write down some novel story, but you don't quite have as much freedom as someone writing a fiction book, because you need it to be consistent with the fundamental laws of physics and with every observation we've made of the universe.
And it also, like, is only interesting if it solves some problem or addresses
Sure.
some need, right?
Yes.
I mean, I wouldn't say it's particularly creative if I just take, you know, Goldilocks and say, for now in my version, it's Goldilocks and the Four Bears. Like, that's not a very good story, right? You know, so we don't just take some theory that already exists and like tweak it.
Yeah.
I mean, unless there's a good reason to tweak it. We're trying to find new novel ways to explain something we don't currently understand.
Yeah, it's a really captivating pursuit, I thought.
I couldn't agree more.
Good, and so maybe this would be a good time to take some questions from anyone who would like to ask Dan anything.
Or Seth.
Any chance dark matter could be antimatter?
So the thing about, so antimatter is kind of the opposite counterpart of every form of matter. So your electrons, which are negative charge, there's something that looks a lot like an electron, but it's a positive charge, we call it a positron. For every quark, there's an antiquark. For a neutrino, there's an antineutrino, and so on. Basically, there's a mirror of every kind of matter that exists. The problem with the idea that antimatter would be the dark matter is we can see antimatter. Like, if there were a bunch of positrons out there, they'd interact with light, they would not be dark at all. So the kinds of antimatter we would know about couldn't make up the dark matter. Now, it's possible that the dark matter is both dark matter and dark antimatter, okay, maybe in equal amounts, for example, or maybe unequal.
So
Yeah.
the motivation to go in that direction.
Yeah. So that's possible. But it's not the antimatter versions of any of the normal known forms of matter.
There's a question right next to it.
Oh, yes. I was hoping you could briefly, to the best of your ability, explain the significance of the discovery of a gamma ray signal in the dark matter.
From the galactic center, that one?
The one you mentioned.
Yeah. Okay.
Was there another one?
Yeah, well, that's the one. So, when dark matter, well, in certain theories of dark matter, or certain classes of theories, when two dark matter particles get together, they can undergo a process we call annihilation. They disappear, and in their place comes energetic, ordinary forms of matter. And those energetic, ordinary forms of matter can be gamma rays. And you'd expect to see these gamma rays mostly from the places where there's the most density of dark matter, and that happens to be in the middle of the Milky Way.
And gamma rays are just photons of a certain energy.
Oh, thank you. Yeah, they're the most energetic kinds of photons. Thank you, Seth.
Is it a sort of a metamorphosis?
Yeah, you could say that.
So
Transformation of dark matter into these gamma rays. Sure.
Yeah, but and that's not particular to dark matter either. I mean,
Yeah.
modern particle physics is sort of a form of alchemy. What we do at the Large Hadron Collider, we collide protons, and the entire point is to see what other particles they turn into when you collide them at very high energies. So indeed, it's amazing that this sort of alchemy, of metamorphosis, it happens all the time.
Mm-hmm. That's right. So, for years, long before this telescope in question went into space and looked at anything, lots of people, including myself, were like working out if dark matter exists and it is one of these kinds of particles, what kind of gamma ray signal would it make? We said, well, it should be brightest at the galactic center, and it should be kind of a puffy sphere around the galactic center. And we said, well, what should the spectral shape look like? What should be the distribution of the photon energies? And it should be something shaped kind of like this. And we said, well, how bright should it be? And based on the abundance of dark matter in the universe, we worked out how bright it should be in these theories. And then this telescope, called the Fermi Gamma Ray Space Telescope, was launched on a rocket and put into orbit. And after a year, its data went public. I downloaded it, and I scrutinized it, and I expected to put a constraint on dark matter, that's what I was setting to do. I was going to write a paper saying, these kinds of dark matter particles can't exist. But lo and behold, there was this really bright signal in the data, unmissable, unmistakable, that had all those three features I mentioned. It had the right spatial distribution in the sky, the right overall intensity, the right spectral shape. And I was like, well, this might be dark matter. I have to write a very different kind of paper. And I wrote a paper saying possible evidence of annihilating dark matter in the black star or something like that. And since then, I've written, I don't know, 10 papers on this data, something like that. And another 1,000 have been written by other people. And in my opinion, it's the most promising provisional signal we have of dark matter's non-gravitational interactions. Could still turn out to be wrong.
Right.
It could be, we're not sure,
Right.
but I think it's promising.
And so the main reason you don't already have a Nobel Prize is a concern about astrophysical systematics, as we say. If there are other astrophysical objects that are made out of normal stuff, but could mimic that signature.
Yeah, what we call backgrounds, right? So ordinary boring stuff making a signal that looks like something really interesting.
Yeah.
That's what keeps me awake at night.
Right. Yeah. It's a more detailed question to really pick this apart.
But if we saw that signal maybe with a more powerful telescope from other parts of the sky, that would be very, very convincing. So it could happen. We have a path forward. Just tell the funding agencies we need to move the Gamma telescope, and maybe that will.
I'm all for it. Yeah. Good. Professor Dasgupta.
Great talks. So, often when we think about life in space, we often wonder if life in space would use the same chemistry as ours, right? So if there are other universes other than the ones that we reside in, then do you think it would use the same physics? Or is it more likely to use the same physics than not? Maybe it's a better question.
That's a great question.
Yeah. Well, so other universes, these are things that were strictly causally disconnected from. So we can't get ever get direct information about what's going on there. But indeed, I'd say the picture now most particle physicists have in the back of their minds, coming at least inspired by string theory, is that in very, very distant parts of the universe of space-time, you do get just entirely different particles. You can get entirely different particles that appear. And so everything, all the sorts of objects that you can have in those places may look extremely different, and there may well be life sorts of processes in those, but look entirely different from us.
If I could just add to that.
Yeah.
So what I meant was that, so like, for example, if you have life that's made of a different chemistry, this is something Richard Dawkins often says, is that if there is alien life, it would still evolve in a Darwinian manner. I mean, if there are things as laws of biology, which we don't think there are at this point, but if there are laws of biology, then alien life would also follow the same laws of biology, even if it's made of completely different matter. So then, if you have different kinds of particles in a different universe, that's fine, but would they still follow some of the basic laws of physics that we know as fundamental laws?
So natural selection is a bit different from what I'd call a physical law.
Sure.
Natural selection is something that happens so long as a few criteria are met in any game theoretic system. So like I could make a bunch of competing computer codes, and these things aren't made of DNA or anything, and yet they will evolve through natural selection. And for this reason, biologists or exobiologists think that if there's life out there in our universe somewhere, it will evolve through natural selection. Like that, anything that we would call life got to be life through that process. And I see no reason to think that would be true across the multiverse too. Now, it might not be made of protons, neutrons, and electrons, or quarks and gluons and electrons, whatever, but it might be made of completely other sorts of stuff. But that stuff, if it can contain information and propagate that information through successive generations with some variation, you're going to have natural selection. So that is kind of independent of the physics or chemistry of the setup you have.
I mean, at its core, all you need is self-replication that is imperfect.
Right.
Yeah.
and then you're off to the races. Yeah, further, yeah.
I just had you mentioned there are 20 known particles more or less that are 15%
Let's
of
count them. Okay,
matter.
so 6 quarks, 6 leptons, and 5 bosons, so 17.
Okay, so if it was much easier if it was 20, then I was going to say if that's 15%, then another 100 would make up the rest of. If there were a bunch of different particles that explain this big chunk of stuff that we don't know, and if that's the case, would you expect like that you could find something?
What if you choose gamma and I choose delta? Will that change the outcome of the
Autonomous recommendations, right?
Yeah, I guess so. I mean, I'd say a very general thing to disambiguate is the technical sense in which physicists mean observer. Observer in this context is not a human or a sentient being. An observer is really any sort of interaction with a classical object that sort of classicalizes the behavior. You say that's a rough.
No, I don't think
No?
so.
Okay.
Yeah. I think this is a big problem with the old Copenhagen way of thinking. Yeah? When you have, there's a classic experiment called the double slit experiment. You have a sheet, 2 slits in it, and another sheet on the other side. And on this side, I'm going to let a particle loose, and it's going to go, you would think it would go through one of the slits and hit the other side. But if they're waves, then in principle they could go through both, and they could interfere with each other, making this distinct pattern. The weird thing is when you did this experiment really, really slowly, only allowing one particle at a time, you still saw the interference pattern. And what this shows is that the particle doesn't go through slit 1 or slit 2, it goes through both. And it interferes with each other, and in the end you get some probabilistic distribution. And that's without any human being in the problem, right? The interactions with the slit don't collapse the wave function. They keep the wave function in its superposition. Or if I do the famous Schrodinger's cat experiment, okay? The interactions that are going on inside the box don't collapse the wave function. The wave function doesn't collapse until you open the door of the box and look.
Sure. Okay. I mean, certainly there's a difference. It's not any interaction.
And like Eugene Wigner famously worried, like, can the cat collapse the wave function? Could a flea on the cat? Could a microbe on the flea on the cat? And like these are like unanswerable questions in quantum mechanics, which is why I prefer the Everendian view, where wave functions don't collapse. We just become part of the superposition. So of the superposition. So when I open Schrodinger's cat's box, now there's a version of me seeing a live cat and another version of me seeing a dead cat. I'm just now part of the quantum plethora of possibilities.
Whoa.
Yeah. There's a beautiful book by Sean Carroll called Something Deeply Hidden, which will convince, I think, just about anybody of this if they take it seriously.
Thank you so much.
Thank you. Okay. Great. Dan, thank you so much.
Thanks, Seth and Dan. Man, wasn't that great?
Yeah.
Wow. That was the first chat, man. That was very cool. I didn't understand any of it. Man, I loved it though. Wow, Seth, that was special, man. I think we got something. You know? Just don't leave. Don't leave town.
Really narrow.
Yeah.
Narrowed down.
Yeah, it's a little old school there. I guess we're gonna do a little Coltrane. And so blues train. It's just the blues, sort of. So we might do, see, the Blue Train, and then, what else was that? Hey, Dan, what else were you thinking about? Oh, okay. We'll do all blues, and then Freddie. Or we'll do Blue Train, Freddie, and then all blues, because we did all blues. You got it? All right. He just played all blues, so let's wrap it up with all blues. Playhouse. And thanks, man. That was brilliant, brilliant.